In this video, we're going to derive the spherical law of cosines. So to start off, we have a sphere sitting on a plane. To help you visualize, I added a little shadow here. So all this is a sphere sitting on a plane, and it's going to be tangent to the plane at a single point. I'm going to hide the shadows for most of the derivation. I can bring them back at the end. But first step here is going to be to add some points to this sphere. So point O is going to be at the center, which is the center of the sphere. And then we have a line extending from O to point C. So C is the point that is tangent to that, or where the tangent plane intersects the sphere. And then the line between O and C has a length of R. In this case, the sphere is going to be a unit sphere, so R is going to equal 1. Just keep that in mind. I'll bring it up later on. Then on the surface of the sphere, we have triangle ABC. The lines between the points are also labeled ABC in blue, green, or blue, red, and green, and we are given angle C, which is an angle between two of the arcs. So you also notice that the sides of this triangle are curved, and that's because obviously they're on the surface of the sphere. Now what we're going to do is we're going to project these lines onto plane P. We're going to use a mnemonic projection, which simply means we're going to draw a line from the center of the sphere through the points on the surface and then onto this plane. So it's going to become clear when I bring up this next image. Alright, so this is the mnemonic projection, and when we do this, we're projecting basically 2 points, A and B. C is already on the plane, so I wouldn't really call it a projection. But we can see that when we do this, we have a projection line like this and a projection line like this. Each of these arcs, say arc B, they are technically on a great circle. So if I draw this out freehand here, the great circle could look something like this. And a great circle is simply the intersection of a plane with a sphere that passes through the center point. And I say plane because it's not just contained in the sphere, it's in this giant plane that's outside of it. And when you project a point on the surface of the sphere onto this tangent plane over here, you're actually going to form a straight line like this. So there's going to be this line carrying all the way through. I can do the same thing for arc C like this. So C's great circle could look something like this. And again, when we extend it out through this plane, we have a plane like this, and it's going to form this circle, or this line here where it intersects, where the planes intersect. Okay. The point of all that is to say that when these great circle planes intersect this plane P here, we're going to have a regular planar triangle. So this triangle here, the sides are not arced, they're straight lines, and we can deal with it using the trigonometry that we already know. One other thing to point out about this is that we have a few angles here extending from the center. So we have angle beta, which is here, angle gamma, which is in the front, and then angle alpha in the very back. I've added a little bit of shading like this to show you this, like the sides of this pyramid that we're kind of forming. So I can pull off the front. This is like the front side of the pyramid, and then we have the side here, and then the back. That blue triangle is like on this blue line, so it's in the same plane as that. Let's put the sides back on. All right, and I'm gonna hide this because it kind of gets in the way. Oops, what did I just do? Okay. So now we're gonna jump into the derivation. I have a little big rectangle here, so I can block out all the different steps. But what we're going to do, the goal of this for right now is to find this length C. So when we draw out the triangle that's on the plane, this is what it's going to look like. And you can, again, it has straight lines. Oh no. It has straight lines for each of the sides, and we have this angle C that's across from side C. Because it's a regular triangle, we can use the regular law of cosines, which is c squared equals a squared plus b squared minus 2ab cosine c. The problem is we don't know what a or b is, so we need to figure that out. And so actually this step, I just show how we're plugging in the values that we have, even though we don't know what they are. And then this step is how we figure out what they are. So in order to figure out what sides A and B are, we can use the fact that this triangle here that I'm shading in is a right triangle, and so is the one in the back that is made by OCB. And so I've basically taken these two triangles out of that diagram and I've put them here. So this is what they look like if we're looking at them from the side. We have a right triangle at the very bottom where the two planes, or where the sphere and its tangent plane come in contact. And then we have the angle alpha and the angle beta up top. And then what we're going to do is we're going to treat each of these triangles separately. Well, not separately. We're going to do the same thing to each of them. We're going to use the Pythagorean theorem to figure out what side B is. So because we know the side is the side R, we have B on the bottom, we can do tangent of beta equals B over R, and tangent of alpha equals A over R. We'll solve for B and A like this. And then, as I mentioned, this is a unit sphere, so R is equal to 1. So we can simplify this to B equals tan beta and A equals tan alpha. So we're doing pretty good here. Now what we're going to do is plug in these values into our law of cosines from before. So let me grab this thing and slide it down. So now we have c squared equals tan squared alpha plus tan squared beta minus 2 tan alpha tan beta cosine of c. And so what I did here was went back up to this triangle, and now we're solving for side C. Zoom back in. Alright, that's the last step of that one. So now, next step, zoom out here, bring this over. Sorry, this is a little clunky, but it helps with explaining. Alright, so now what we're going to do is we are going to look at a different triangle that shares this side C. And that triangle is going to be the one on the front face right here that I'm shading in. So the two lines that get projected down, they form another triangle. So again, we're going to use our law of cosines to figure out what side C is. And so here, just to help you visualize, I drew out this triangle on the front. Again, for the sake of being clear, it's this triangle here. And the interesting thing, and a very useful thing, is that the line that extends from the center of the sphere and intersects with the tangent plane, so this line and this line, those are both secant lines, and they're defined by the angle that they're formed by. So we have alpha in the back and beta in the front. I can put a helpful link in the description of this video to help you see what a secant line is. But for the sake of this derivation, we know that x is equal to secant beta and y is equal to secant alpha. Okay. Now we can sub in the values that we need into our law of cosines. So c squared equals secant squared alpha plus secant squared beta minus 2 secant alpha secant beta cosine of gamma. And so we are using everything that we're given in this triangle to solve for this law of cosines. We have side C across from angle gamma, so we're using that. Then what we're going to do is we're going to take the formula from the first part, this one where we also solve for c squared, or c, and we're going to subtract it from the equation we just found. So when we do that, we get this giant statement here. I'm not going to read it all out because it's a lot, but we can use a trig identity, which is 1 equals secant squared theta minus tan squared theta, to simplify this. So here what we have is we have two pairs of secant minus tan secant squared minus tan squared. First one is secant squared minus tan squared alpha, and then we have secant squared minus tan squared beta. And so both of those just turn into 1. So the equation becomes this. Zoom in a little bit. 0 equals 2 minus 2 secant alpha secant beta cosine of gamma plus 2 tangent of alpha tangent of beta cosine of c. So we're getting somewhere. Now what we're going to do is we're going to try to solve for cosine of gamma. So what I did here was just bring this, oops. Okay, not cooperating with me. So all I did here was I took this portion of the formula and I brought it to the other side. And then I'm going to divide by 2 secant alpha secant beta to get cosine gamma alone. Keep going down. And then this is what we're left with. And then we can separate it into, we can separate the right side into two different elements. So 1 over secant alpha secant beta plus tangent of alpha tangent of beta cosine c over secant alpha secant beta. All right. Next step is to turn the right side into terms of just sine and cosine. So I do a little bit of like work here to show how it works. Work to show how it works. Yeah, so for the first element here, just grab a different pen. This whole equation or function here is equal to 1 over cosine of alpha, 1 over cosine of beta. So yeah, secant is 1 over cosine. And so let me just move down and actually it'll help to see what happens. So the whole first element here turns into cosine alpha, cosine beta. And then for the right side, tangent of alpha over secant of alpha, that just becomes sine. And so I showed how that works here. And we have two pairs of this. So we have the alpha pair and we have the beta pair. And so the right side just becomes this, sine of alpha times sine of beta. And then we have cosine c. And so we're not quite done. As I've mentioned several times, we're using a unit sphere, so r equals 1. And when r equals 1, the arc length of a side of the spherical triangle equals theta times r, which is theta times 1, which is just theta. So what we can do is we can replace gamma here with the side length that it's across from, which is c. So this is the spherical law of cosines here. Cosine of c equals cosine alpha, cosine beta, plus sine alpha, sine beta, cosine c. And so if we go all the way back to where we started, what we're really proving or showing is that if we have a triangle on the surface of a sphere, like we have here, and we know two of the sides and the angle between them, so a side angle side spherical triangle, we can figure out what the missing side is using the angle across from it. So in the next video, I'm going to go through some practice problems, but yeah, this was a pretty fun derivation.